Now that we've taken a good look at how linear functions work, both as equations, tables, and graphs, now we're ready to look at how we can model real-world situations using linear functions. And just by way of a quick reminder, some things to remember as we do this. Our general formula for a linear equation is y equals mx plus b, where the m is the rate of change or the slope, and the b is the initial value or y-intercept. Sometimes we have to do a little bit of work to find the b. Also, sometimes we have to do a little bit of work to find the m. The way we find the m, the rate of change or the slope, is we can take y2 minus y1 over x2 minus x1. If you can remember that information, you can probably solve just about any linear function problem you come across with in any context. But let's practice a few together. Let's take a look at some examples. We're going to start with a database manager. Notices that 1.2 million rows have loaded from a large file backup. After 10 minutes. Later, after 20 minutes, and that's 20 minutes total, he notices 2.5 million rows. Have loaded. We want to know, or the database manager, she wants to know how much time is needed for all 80 million rows. Well, let's find out. First thing we want to do is establish two coordinate points that can help us build this equation. What we notice is that 1.2 million rows were loaded after 10 minutes. And so if 10 minutes is my independent variable, we get 1.2, and we'll leave off all the zeros and just know that our rows are in millions. For our second point, we see that after 20 minutes, there's 2.5 million rows. Notice we've got x and y on both of them. Both of the x's are the amount of time, and both of the y's are the amount of rows. That needs to be consistent, that the rows are always second in our points, and that the time is always first in our points. So now we can find our slope from this, which is y2 minus y1, 2.5 minus 1.2 over x2 minus x1, 20 minus 10, gives us 1.3 over 10, or 0.13 for the slope. Now we don't have the y-intercept right now, so we're going to have to do a little bit of work to find it, but we can plug it into our y equals mx plus b formula using one of the points. Let's just go ahead and use the first point, where y is 1.2, the slope is 0.13, the x is 10, plus b. And so we get 1.2 is equal to 1.3 plus b. Subtract the 1.3 from both sides, and we get 0, negative 0.1 is equal to our b. So now we know that our equation is y equals m, the 0.13, that's the rate of change of this file backup, x minus 0.1. Now that we've got our equation, we're ready to actually answer the question that's being asked to us about the 80 million rows. So the first thing we need to know is which x or y do we put the rows into? Well, remember we said the rows were y, and I said it has to be consistent. So here again, our rows are these 80 million rows is equal to 0.13x minus 0.1. And we just have to solve this equation. We'll add 0.1 to both sides, and we get 80.1 is equal to 0.13x. Divide both sides by 0.13, and x, the amount of time is needed for all 80 million rows, can be found just by dividing 80.1 by 0.13, and we get 616.2 minutes, making sure we put labels on it. So after 616 minutes, a little more than an hour and a quarter, a little more than an hour and a quarter, it's going to take for all 80 million rows to compile. Let's take a look at a second example. Let's say the population of a town in 2004 is 6,200. By 2009, it grows to 8,100. We're going to do two things. We're going to predict the population in the year 2013 and when the population reaches 15,000 people. So again, we need to start with some points. We could use our year 2004, matching it with the 6,200, but sometimes it's easier if we just say, we're going to say time starts in 2004. So that way year 0 will represent 2004. And what's really nice about picking a nice convenient year 0 is the other number, the 6,200, then's also going to become my y-intercept, my b. For my other point then, 2009, I see that's 5 years after the beginning of time. And the population there is 8,100. Again, notice we put time in first on both of them. Time is our x. Population on both of them is our y. So when we set up our slope, y2 is 8,100 minus 6,200 over x2, 5 minus x1, 0. Gives us 1,900 over 5, or 380. We now know the equation we want is y equals m, 3,800, or 380, times x, plus b, our y-intercept. And the nice part about picking time 0 is we know the y-intercept is 6,200. All right, we're ready to actually answer now the two questions the problem asked us. First, it wants us to predict the population in 2013. 2013 is a time, it's a year, so that's going to go into X. But remember, we want the number of years that have gone by from 2004. Well, 2013 is 9 years after 2004, so we have y equals 380 times 9 plus 6,200. And that you can just put in your calculator. 380 times 9 plus 6,200 is going to be 9,620 is the population in the year 2013. Now for the second part of our problem here, we want to know when the whole population reaches 15,000. Now we know with the population, we said that was our second variable, our y. So we're going to say y equals 15,000 and plug it into that same equation we just found. So y is 15,000 equals 380x plus 6,200. And then we just have to start solving this equation for x. Subtract 6,200 from both sides. That's going to give us 8,800 equals 380x. Divide both sides by 380. And x is equal to 23.1. But we need to be careful here because 23.1 represents the number of years that have passed since time began. Time began, we said in 2004. So actually, to figure out the year, we're going to take 2004 and I'll add the 23 to get 2027. During the year 2027, the population of this town will pass 15,000. Let's do one last application problem together before I give you a chance to practice modeling some of these on your own. Let's say you are deciding between two moving companies. The first charges a $20 fee plus, I'll just write 59 cents per mile. The second charges a $16 fee. Well, that sounds better. Plus 63 cents per mile. Oh, that sounds worse. When is it better to pay the higher fee? Well, we've got two things happening here. We've got company one, the first company, which has a rate of change of 59 cents per mile, making everything into dollars would be 0.59, and a starting value for a fee of $20, which means the first equation is y equals 0.59x plus 20. Y equals mx plus b. The second company has a rate of change of 63 cents per mile and a starting amount, our B, of $16. So the second company's equation is y equals 0.63x plus 16. What I want to notice though is both of these equations, both equations are equal to y. If they're both equal to y, then they also are both equal to each other. 0.59x plus 20 is the same as 0.63x plus 16. Because if they're both individually equal to the same thing, they're both individually equal to each other. And that gives us an equation we can solve for x, where x is those number of miles that we're going to be traveling. Recall that when the variable is on both sides of the equation, we can move the smaller one first by subtracting 0.59x from both sides. Leaves us with 20 equals 0.04x plus 16. And now I can subtract 16 from both sides, and 4 is equal to 0.04x. Divide both sides by 0.04. And when I do that, x is equal to 100. So when are they both the same? Well, I'm sorry, when is it better to pay the bigger fee? After 100 miles. After 100 miles, it's cheaper to pay the bigger fee because your per mile rate is smaller. These application modeling problems can come in lots of different types, styles, and forms. What we know, though, is the same for all linear functions, is that y equals mx plus b, where m is that rate of change or slope, b is that initial value or y-intercept. We also know the formula for the slope. If you have 2 points, you should be able to use those things to answer any modeling problem with a linear function. It's your turn to practice. Good luck.